University of Michigan last year, and her research pertains to investigating the evolution of plasma from the sun by studying heavy ions in the solar wind and transients. In the past, she has simulated the non-equilibrium ionization evolution of ions in a coronal mass ejection and the solar wind between the sun and interplanetary space to investigate the thermodynamic conditions that reproduce ion observations. Presently, she's investigating heavy ion depleted plasma measured near the Earth to understand the mechanism responsible for the absence of selected charge states in the heliosphere. Additionally, throughout her postdoctoral appointment at the CfA, she plans to investigate heavy ion signatures in the solar wind with Solar Orbiter's heavy ion sensor and Parker Solar Probe's SPAN instrument. And today she will tell us about the solar origin of anomalously low bare ion densities in the solar wind and ICMEs. So take it away whenever you're ready.
Oh, thank you. So that's, I mean, you essentially described everything I was going to say. That's so funny. So yeah, so like Paul was saying, so we've been looking at these periods of solar wind where we find this very low density of bare ions. So the bare ions are essentially those fully stripped of electrons, like carbon 6+, nitrogen 7+, oxygen 8+, and all the ones that we can essentially resolve with our mass spectrometers. So we have these periods in the solar wind and in coronal mass ejections where these densities are very low compared to just typical solar wind and ICMEs. And so the work is essentially trying to take these periods and trying to map them or sort of link them back to the sun, certain structures at the sun, to really understand their formation, how they're released, and sort of how they come to have this very low densities of bare ions. And I do have to apologize. I'm sick, so I'm probably constantly going to be clearing my throat. So with measurements that we make of composition, of ion and elemental composition in the sun, generally both of these properties are pretty much set a few solar radii from the sun. So what we're measuring in the heliosphere is pretty representative of the properties in the corona and also the properties that sort of set elemental composition back at the sun. So for instance, the ion freezing distances, usually the ions freeze in within a couple of solar radii from the sun. So for those of you maybe not so familiar with this term, ion freezing, so generally when plasma is released from the sun, it sort of expands very, very quickly. Density sort of drops very fast. And the ionization recombination processes become less and less effective as you get farther and farther from the sun. And so depending on what ion you're looking at, the sort of freeze-in distance, the distance in which the ions become fixed and are no longer changing, is roughly between 1 or 5 solar radii, depending on what ion you're looking at and the properties, the electron properties of the plasma. And then in terms of the elemental composition, so the FIP effect, the first ionization potential effect, is pretty much governing the fractionation of the plasma that we observe in the heliosphere. And so the FIP effect is happening pretty much between the chromosphere and I would say the interface towards the corona, so lower in the corona, so that particular region of the sun. While gravitational settling is, I guess, not as effective at fractionating the plasma at those distances, but becomes more and more important as you at higher, I guess, altitudes in the corona. So in this case, so this figure here from HAO 2020 showing the effects of gravitational settling roughly about 1.5 solar radii or so. And we've seen this in big coronal loops and helmet streamers, gravitational settling becoming important. And also Coulomb drag. So once the plasma leaves the sun, it's theorized that Coulomb drag can also fractionate the plasma that we measure in the heliosphere. And also, so when the solar wind transitions from collisional to collisionless, which happens in the corona, very low in the corona, wave particle interactions and turbulence to become important mechanisms for translating energy to the particles to either heat them or accelerate them away from the sun. And so I would argue that this is happening fairly close to the sun and happening throughout the evolution of the plasma, throughout throughout the heliosphere. And so when we see, for our particular case, where we see this long-term deviation of these compositional trends, either in ions or in the elemental composition, which is pretty much set by the Fipp effect, these long-term deviations then can tell us a little bit about non-thermal processes taking place in the plasma, whether it's wave particle interactions or gravitational settling or Coulomb drag being important in certain solar wind streams. So an example of that, and this was a case where there was instances where we find iron to hydrogen or iron to proton, these periods where there was a depletion of iron compared to what we typically expect in the solar wind. So if you sort of ignore these panels and look at oxygen to proton versus iron to proton values, we have these periods where you have this huge depletion of iron, several orders of magnitude less than what we see sort of upstream and downstream. And we also see a little bit of that effect in the oxygen as well. So when they took these periods that were identified with these iron depletions, they found that these periods were, that iron wasn't the only element that was affected. Other elements were affected as well, and they were affected in a mass dependent way. So such that the helium, so lighter ions lighter elements like helium were less affected than heavier elements like sulfur and and iron. So these iron to proton dropouts that were found in the solar wind were evidence of gravitational settling from these large loops back at the sun that were being measured in situ. Okay. So similarly, what we find is there are these periods in the solar wind where the C6 plus density is very, very low. And so these periods were essentially discovered when looking at plots of C6, C65 to 0706. When you look at them in sort of a time series form, and I'll show a couple of examples, it's easier to sort of spot, but there are periods where C6, C5, this ratio becomes completely uncorrelated to 0706. And almost anti-correlated in certain instances. And it's the outlier wind, which this is sort of labeled as the outlier wind. And I interchangeably say dropout events, but they sort of mean the same thing. And so here is the outlier event. So it's much easier to see when we look at a histogram that looks like this. So this is just a 2D histogram of C65 to 0706. And these are just counts, right? So we see most of the solar wind sort of lies along a positive trend, right? So when C6, C5 increases, we expect 07, 06 to sort of increase as well. And the outlier event doesn't follow that correlation. We have a C65 value that's much, much lower than what we expect for the 07, 06 value that we see. And you can sort of think of the lower left part of that plot as the fast solar wind. So fast, tenuous, less ionized material. And as you get to the upper right corner of the plot, that transitioned into slower, denser, more ionized solar wind. So you can think of the outlier event as sort of the subset of slow solar wind. And this is, so there have been studies looking at the properties of the outlier wind, both in in the solar wind and in ICMEs. So generally when we compare our outlier plasma here to the slower solar wind non-outlier plasma, what we see is that the outlier wind is generally denser compared to slow solar wind. It's traveling, it has a mean speed that's slower. It's much, much cooler than the slow solar wind, the proton temperature. It has a slightly more elevated helium to hydrogen value, and the magnetic field is roughly about the same. And we see the same when we compare the outlier ICME periods to just non-outlier ICME periods. And like I was mentioning before, C6 plus isn't the only ion that's affected. We see depleted ions of mass per church 2 overall depleted during these outlier events. So we see C6 plus, that's very low compared to what we typically expect that to be. Let's see. So the work that we were doing is sort of extending this a little bit and stepping back to look at the properties of these outlier events, event by event. So we were aiming to see if maybe some of the features that we would look at in these time series forms in individual events would sort of stick out as features that might be interesting to connect back to the sun. So I have a couple of examples of the outlier wind. So this is an example for the solar wind. So in this case, like I was mentioning before, it becomes really easy to spot the dropout periods when you look at them, when you look at a time series of them. So the blue here is 0706, the red or this orange is C65. And you have this period where this value completely drops, and the 0706 sort of continues unaffected, and in this case, slightly anti-correlated to the C6, C5 value. And so I will mention that there are, between the solar wind events, which I've sort of separated them to see if they're related mostly, but we do find that a lot of the features that we see in the solar wind events are also, they're also observed in the ICME events. It's just, they tend to be a lot more clear in the solar wind events. But so panel B, here I'm plotting the plasma beta and helium to proton values. This is the higher resolution stuff is from SweetPam. So in this period, we typically see high plasma beta. We see a slightly elevated helium to hydrogen value compared to immediately upstream and downstream. So this is the proton velocity here, and this is the proton density. Like we saw in the table before, typically the outlier wind is in very, very slow moving wind. But one of the things that we weren't able to see when we look at the statistical values of just the outlier periods was that they're generally sort of at this valley of the proton speed, right? Generally surrounded by faster streams, upstream and downstream. And they're generally associated with some density enhancement, some proton density enhancement. In terms of the magnetic field components, we see an increase in the magnetic field fluctuations downstream of the outlier events compared to upstream. So the increased fluctuations in the magnetic field is really interesting because we also see this in the velocity of the solar wind. So this is interesting because these sort of increased fluctuations indicate that we're going from, or at least correlated fluctuations between the velocity and the magnetic field. They give us an indication that we're sort of moving into more alphanic solar wind, which may be related to its formation process. And then the last two panels are probably the most interesting and the most common between the solar wind and ICME events, where nearly all the events are associated with some rotation of the magnetic field, whether it's a nice smooth rotation like we see here, or just a sudden jump in the magnetic field. And then in terms of the electron straw, so this is electron flux, superthermal electron flux. So if you see, the way that I sort of think of this is, if you do see an enhancement between 0 and about 45, this is an indication of sort of field-aligned electrons, right, heading from the sun out into the heliosphere. And 180 degrees from that is the opposite direction, right? So you have electrons, field-aligned electrons headed back to the sun. So in this case, although it looks like the electrons are changing directions, this is actually just right, due to the rotation of the magnetic field, where in this case the electrons keep flowing in the particular direction. So you have this unidirectional straw that changes directions, and magnetic field changes directions, so the flow goes the other way. All right, and then this is an example for the outlier inside of a coronal mass ejection. So the ICME boundary here is in the blue, and then the dropout event is in the purple. So like I mentioned, the properties and these features are fairly similar between the two, but I will point out in the case of ICMEs, you typically don't see a high beta. Typically it's a very low beta, which is the opposite of what we see in the ICME events. And also we do see an elevated helium to hydrogen abundance in the outlier events related to ICMEs. And it's really interesting too, because typically an elevated helium value is typically associated with ICMEs, so that's not new. But typically those periods are also associated with these outlier events. So that might be an indication of sort of the source region back at the sun. In terms of speed, it's not really in terms of, in these ICMEs, they're not very speed dependent. Typically, you do see some enhancement in the proton density compared to immediately before, but not necessarily a huge enhancement like we see in the solar wind events. In this case, we do see an increase in magnetic field fluctuations like we saw in the previous example, but this is sort of a 50-50 chance. It's not so clear that the magnetic field fluctuations are related in this case. But the two features that we continue to see in both events and are common to both events is the rotation of the magnetic field, which we see again. And then in this case, we see a little bit of sort of intermittent bidirectionality of the electrons. So these features, the rotation of the magnetic field, the bidirectional or unidirectional straw, or a straw at all in the electrons, are very common features that we use to identify ICMEs at 1 EU, these large-scale ICMEs. But there are also common features to heliosphere current sheet crossings, where you're going from essentially one magnetic sector to another, right? You're crossing the plasma sheet, where it's typically associated with this density enhancement that we see here. We see a rotation of the magnetic field, right? We're moving into different sectors, and we also see, and we expect to see, an electron straw associated with the big streamer structure in the heliosphere. Like I mentioned, or I didn't mention this before, but typically the outlier events, both in the solar wind ICMEs, are very short. The majority of them, I would say, I think roughly between 70 to 80% of them are less than 10 hours long, so they're very, very short. The ICME events tend to be slightly longer, but they're still, the majority of them are less than 10 hours. And they're also very strongly solar cycle dependent. So here, what I'm plotting is just the number of events across different years. This is across solar cycle 23. The red is the smooth sunspot number, and I plotted here all of the dropout events, as well as all the ICMEs in the orange, all the ICMEs that are on the Richardson and Kane ICME list for this particular time frame. I've also separated the outlier events from the ICME to solar and the solar wind events to sort of show that they're both sort of independently sunspot solar cycle dependent. So they both follow the sunspot number fairly well independently, which is really interesting. This sort of tells us that the outlier events are very intimately connected to magnetic activity at the sun, the magnetic field, and also that they're very connected to each other, which we really didn't know before. Okay, in terms of the composition, so you saw this plot before, the outlier plasma being down here. I've also split up this this plot between region 1 and region 2. The reason I split it up in this way, so this being the outlier plasma, everything up here being region 1, I split it up this way because I wanted to compare the outlier wind directly with the plasma right above it, because the outlier wind, with the exception of C6 being low, that's the only real difference that we see in this plot between this plasma and this plasma. So it'd be really interesting to compare the features of these two types of plasma. And then region 2 is essentially the rest of this plot, which is here. So if you remember, you have sort of faster wind down here to slower wind up here. And you can sort of think of region 1 as slow wind, very loosely slow wind, and region 2 as fast wind. So the outlier plasma is here in the purple. What I'm plotting here is just the composition compared to oxygen, and it's organized by the first ionization potential. Low FIP ions being here, I've separated this as sort of the mid FIP ions, and then high FIP ions are here. So what we see is that the outlier plasma is generally more low FIP enhanced compared to region 1, so compared to slow solar wind, which is by itself not very interesting. But one of the things that sort of stood out from these measurements is, so we see a very large depletion in the carbon, and this is carbon to oxygen. And this is sort of expected since a large amount of the composition is missing, right? C6 plus in this very highly ionized plasma is missing ultimately. So that's a big part of the contribution that contributes to the composition. So that's sort of expected. We find that sulfur is much more enhanced compared to the slow and fast solar wind. So sulfur is interesting because it tells you from the description, this Puntamora force description of the FIP effect, it gives you an indication of the magnetic topology of where this plasma came from. So in plasma sort of emerging from open field tends to be the sulfur acts more like a low FIP ion versus closed field. It acts like a high FIP ion essentially. So in this case, in the outlier plasma, we see that the sulfur acts like a low FIP ion and possibly coming from open field at the sun. And then another interesting compositional feature of the outlier wind is that it's enhanced. It's enhanced incredibly of neon. The neon to oxygen value is roughly about 0.4. And this is a value that we often don't see in the thermal solar wind. So as shown here, this is a value though that has been quoted in as the composition of helium-3 rich SEP events. They find that the neon to oxygen of these energetic particles is typically about 0.42 or so. This is also a value that's been seen in during flares, and this makes sense that they would both be roughly about the same, because presumably the flares are the seed population of the SEP particles. So that makes sense. but we never really see this high of neon in the thermal solar wind. So this was really shocking because we see this not only in the solar wind, but also in the ICME events, which shows that the outlier events are maybe somehow related to flares or even related to the way that maybe reconnection, maybe the way that they're released into the heliosphere is related to the way that sort of flare, what's happening in flare regions. Another sort of interesting compositional signature is when we look at neon compared to magnesium, this value is roughly about 1.8. And this is a value that's been seen in several prominences, the composition of several prominences in the past. So again, this is really interesting because we've sort of related the solar wind events to these ICMEs. Maybe what we're looking at are smaller scale ICMEs or maybe prominence eruptions or something like that. But we really can't tell. Okay, so from the compositional signatures then, we've tried to compare with some of the studies that have been made taking these solar wind measurements at 1 AU and essentially back mapping it to structures at the sun. So in particular, this Liang's study in 2017, what they've done is they've taken these solar wind periods at 1 AU and they've taken these chunks and ballistically back mapped to a source surface and then traced down the magnetic field lines down to particular structures at the sun. And they sort of have come and they came up with six solar wind types coming from 6 different sort of locations at the sun. So helmet streamers, active region boundaries, and so on. And when we compare the composition of our outlier wind to what they find for helmet streamers and active regions, so it doesn't quite fit exactly, but we're most similar to plasma that's being released from helmet streamers and active regions. I think they've made the distinction of active regions because there doesn't necessarily have to be an active region at the base of a helmet streamer. But we're most similar to these 2 solar structures. And then similarly, in a different study, in this 2015 study, what they've done is similarly, they've taken Alphen speed, entropy, and the proton temperature. I don't remember the details of this paper, but they've come up with 4 different solar wind schemes. Ejecta, which is essentially just CMEs, coronal hole, streamer belt, which are pseudo streamers, and then this sector reversal region, which is related to the helmet streamer structure. So when we look at the entropy of the outlier wind and the Alphen speed of the solar wind, and we saw the proton speed being the proton temperature being very, very low in the table. These values match up with this purple and the purple and this blue solar wind type. The sector reversal region, again, linking it back to the helmet streamer and possibly even the active region below that. So these 2 studies essentially have linked to the outlier wind that we see through the compositional measurements and these other properties, have linked them to helmet streamers back at the sun. And it sort of ties back to the idea, like I was saying before, that we think, at least it's a lot more clear in the solar wind case, we think that the solar wind events are happening at these sector reversal regions, happening at the plasma sheet, maybe having these maybe related to eruptions, these small flux strobes traveling along the plasma sheet, or maybe due to the actual the big streamer itself, which is very interesting that we sort of came to this conclusion with these 2 studies. So just to summarize all these properties that I mentioned, since there are a lot of them, and sort of synthesize a little bit about what this tells us about the formation process, where the outlier wind is originating from at the sun. So we showed that the events are generally solar cycle dependent. The composition, the entropy, alpha speed, all link them to streamers or active regions at the base of helmet streamers. The superthermal electron signatures, they indicate that the plasma is sort of traveling within this larger structure that remains rooted at the sun. And also we see this change in the magnetic field direction, which is an indication of either a flux trope or some sort of change in magnetic sector of the heliosphere. We also see that they're fairly short, both in the solar wind and ICME events last less than 10 hours for the most part. So what this tells us is that this outlier wind seems to be strongly governed by magnetic activity. It's likely released through reconnection, given their connection to helmet streamers and active regions, likely embedded in this very large magnetic structure rooted at the sun, either in the case of ICMEs, this flux trope, or the streamer structure. And we may be its duration and its magnetic field rotation and the superthermal electron may also be signatures of a flux trope itself, a flux trope topology. So what we hypothesize about the outlier wind formation is that we think that these are smaller scale eruptions that are happening at the sun. They're releasing these blobs of plasma, maybe flux tropes of plasma that then are traveling along the plasma sheet. And so this isn't a new idea. This is something that's been hypothesized in MHD simulations. Helmet streamer tips are sort of ideal, have ideal conditions for reconnection and sort of ideal places for this sort of release mechanism. And this is also the observations, or this, I guess, hypothesis is consistent with other observations at magnetic fields, magnetic sector boundaries that found these flux tropes traveling along the plasma sheet. So maybe, so what we think is happening is, so this is a large streamer, in the case of a large streamer, where the source is a helmet streamer. So we think that the plasma is either released through some sort of eruption at the base of the helmet streamer, maybe a filament eruption, or at the streamer cusp. Regardless, I think, of their release, we would still find very similar signatures that are being measured by the spacecraft, I think. So then the structure then gets released into the plasma sheet. It travels along the plasma sheet. And what we're measuring when we cross this, when we are crossing the heliospheric current sheet, are either these flux tropes traveling along the plasma sheet or something else, or just part of the streamer blobs that are being released at the tip. And so as we cross then the heliospheric current sheet, we would be traveling from faster solar wind into slower solar wind. We'd find a density enhancement because of the plasma sheet. And we generally would find superthermal electrons, some sort of straw that's associated with this larger streamer structure. And so I think we sort of hit the limit as to what we can say about the outlier wind from 1AU measurements. I think moving forward, we really need to look at less evolved material inside 1AU so we can see whether, if it is related to some prominence eruption or some ICME, we can see some of these features a lot clearer and a lot more coherent in less evolved solar wind. Also, its unique compositional signature, if you remember, high sulfur, low carbon, really, really high neon abundance, might be worth looking at the sun. And then the last thing is Ultimately, we do want to know what the process is that's causing these low densities of baryons that we measure in the heliosphere and the outlier wind. And so what we've done with this paper is we've tried to constrain that a little bit. Is it an eruption? Is it a flux trope? There is a sort of a complementary paper that's happening, being led by John Raymond, sort of from more theoretical perspective about, maybe waves having influencing the plasma in a mass per charge way, such that certain ions are being accelerated versus others. And so hopefully we'd be able to constrain some of the process in which the outliers form back in the sun to help sort of guide this paper to really answer this question. And so I'll end here and I'll take any questions. Thanks.
Thank you. Do we have any questions for Yeimy? Maybe I can start then. So you say that these events are correlated with helmet streamers. Are you basing that just on the kind of statistical evidence of what the composition of helmet streamers looks like from that work you showed from HAO, I think? Or are you actually able to take any specific events from your list and trace the field lines back to see where you think it comes from?
Yeah, so we can do that for individual events. I think that would be really interesting. I did run an MHD model that sort of showed we were at the sector boundary for several events. I didn't include it here, but that was the first sort of indication that maybe we were looking at stuff coming from streamers. And also, so that sort of guided the thinking here, right? We initially didn't know what this was, but these are actually very strong features of heliospheric crossings. Like I said, particularly these two panels here being present in almost, we looked at over 600 events, and this being sort of a prominent feature, or these two features being very prominent in nearly all the events. That's sort of what's sort of guiding the idea that we're connected to a streamer. But this was sort of more supporting evidence that people statistically, right, has been shown before, that this sort of composition tends to be linked to this structure at the sun.
Anyone else have a question?
I was just going to say a follow-up to that would be maybe could you use Parker data? Because they do a lot of tracing, or they seem to do. The talks I've seen from them, from people analyzing Parker data, is they show they can trace. They sometimes trace back to the sun, to specific structures on the sun, what they see. So I thought it could. You mentioned in the conclusions you're looking at it now, so I was wondering if you could use Parker to prove that a little more.
Yeah, that's exactly. I mean, HIS is going to be easy, right? HIS has a compositional instrument, so we can actually identify these dropouts with that compositional instrument. It would be, I think people think that there have been several heliospheric crossings with Parker Solar Probe, but like I said, it's really hard to tell whether we're actually we're actually looking at this outlier event without compositional data. And this is where I think Solar Orbiter is going to be very useful.
So Parker doesn't have the compositional.
No.
I didn't know that. Thank you.
Yeah, no, it's I was gonna have a snide remark about that, but I think people are sick of saying, or of hearing me say that. Yes, Parker doesn't have a compositional instrument, but Solar Orbiter does, and it's going to get to 60 solar radii. So,
okay, anyone else? If not, then thanks again. Thanks everyone for coming, and thanks.
Yeah, thank you.
Thanks, Yeimy. Good to see you.
Thanks, Yeimy. Good to see you, mate. Feel better. Sorry about that.